Today we are going to talk about interference in wedge-shaped thin film. In previous classes we have studied about interference in a thin film whose thickness is constant. Now we are dealing with a film, a thin film whose thickness is not constant. The thickness will vary from one point to the other point. So here's we have a wedge shaped film. So this is how we can form a wedge shaped film. For that you have to take two glass slabs and you have to put one glass slab on other. So here's I have two plates. Okay, so to form a wedge shaped air film in between these two glass plates, what we have to do, we have to put something in between these two glass plates so that we can form a thin wedge shaped air film. For this purpose here I have used a cap, a pen cap. You can use actually to see the interference pattern due to this thin wedge shaped film, we have to use a very minute, a very thin material, a very thin kind of thing. If we can use some human hair or paper, any kind of small thing. Why? Because to have the interference pattern due to the thin film, I told you in my first class, interference due to thin films, I told you there is a condition to have an interference due to thin film. That is, you should have certain thickness of thin film, then only you can have the interference. If the thickness is exceeding that particular range, then you can't have the interference pattern due to the thin film. So that's why you have to put something which comes in the range of some order of wavelengths, then only you can have the interference pattern due to this thin film. So we can have a look. This is the one slab, glass slab, and this is the other glass slab. And because of this cap, what we got some angle between these two glass slabs, and because of that angle there is a air film formed between these two glass plates, and that film is having zero thickness at this end and having some thickness at the other end, and the thickness of this air film is gradually increasing as I move from here to there. So this particular film which we formed is called a wedge shaped thin film. So today we'll study the interference pattern due to the wedge shaped film. So let's get started. So here's I have one glass slab and the other one on it, making some angle theta. This angle is coming because we are putting something in between these two glass plates. Okay, so the monochromatic light source we are incidenting, the monochromatic light source is hitting on the top surface of the first glass slab. So usually most of the teachers directly they will explain you something like this. They'll take this as the first slab and the other slab, and they'll take some angle between them, and they'll directly, this is the incident light, and they'll take directly this as the reflected light. But this is not the case. Actually, from this first slab, the top surface of this first slab, there is a first reflection which this ray will not take part into the interference phenomena due to the wedge shaped film. Now after this is the incident ray, and part of it got reflected from the top surface of this glass plate. The remaining light will, so here's the rarer medium and this is the denser medium. This is the glass, this is the air, and the film which we formed, the air wedge shaped film, is a air film. Okay, now again from here, this part of the incident ray will get transmitted, and from the bottom surface, you see the normal will come perpendicular to the bottom surface of the glass slab, and from here part of this transmitted light which transmitted inside the glass slab will get reflected from the bottom surface of the glass slab, or we can say that top surface of the thin film, the air thin film, from the top surface, this ray will get reflected, and again from here the ray will come out something like this. So the reflection from the top surface of the air wedge-shaped film, the reflection is happening. This first ray is undergoing reflection from denser to rarer medium. This reflection, I'm calling it as R1, and again the part of this light ray will get transmitted inside the air film, air wedge shaped film, and now this again from the top surface of the glass, or we can say that from the bottom surface of the air wedge, one more reflection, this light ray will get reflect, and from here it will get transmit, and it will come out something like this from here, R2. So this is the reflected light ray from the top surface of the air from the wedge shaped film, and this ray too is from the bottom surface of the air wedge shaped air film. Now we have these two light rays, and these two light rays will undergo interference. Now we have one more, the most important thing to notice, and so many students will get these kind of doubts, is that this is also a kind of film, and this is also a film. So it means if you're seeing an interference pattern here, it means the interference pattern is due to the first glass plate and the second glass plate, and it is also due to the wedge shaped air film. So the thing is, the interference which we are observing here, it is only due to the air wedge shaped film. How come we are just seeing because of that? Because the thickness of this glass and this glass is large as compared to the thickness of this air wedge shaped film. This thickness is small, that's why these two reflected light rays are near to each other, so they can interfere. Okay, but you see, when it comes to seeing the interference due to these two light rays, they are too much apart from each other. They are not you see, the distance between them is too large. Why the distance between these two reflected rays, the reflected ray from the top and the reflected ray from the bottom, due to this glass slab is large? Because its thickness is large. If you make the thickness small, you can see these two light rays together, but now you have taken its thickness large as compared to the thickness of this air film. So because the air film thickness is less, that's why these two light rays are near to each other, they can have the interference phenomenon. So the interference which you see, which you will observe at the end of the day, that is gonna be only due to the wedge shaped film, not due to the glass slabs which is on the top or the bottom. Again, these two rays are, there's so much distance between them, so the interference which you are gonna see is due to the air film only, not due to the glass slabs which we are using. So that's why the condition is that to have the interference pattern due to the wedge-shaped film, what is that thing? The thickness of these glass slabs should be large as compared to the thickness of this air film. Then only you can have the interference due to the wedge-shaped film. Now, for the explanation purpose, I will be using this diagram, but this is the actual picture. This is the actually, indeed, what is happening is this is not the reality, but only for the geometrical purpose, only for the understanding purpose, I'll be using this diagram from now on. So here's my, so this ray is my R1, this one, okay. This is getting reflection from the boundary between denser to, so it is getting reflected due to the rarer medium. This is the air medium. Okay, now the incident angle is I. Now the transmitted light ray, this is the transmitted light ray, and again from here the light will get reflect. This is, I'm calling it as angle of refraction R, and again from part of this transmitted light ray will get reflected due to the bottom surface of the air film. Now from here this light ray will come out. There's one more thing that we can notice here. In the previous classes, the reflected light rays which we are getting, the reflected light rays were parallel to each other. Now we can see that these light rays are not parallel to each other, they are diverging. If now to have the conditions for the interference of dark and bright, we have to find out the path difference between these two reflected rays. The reflected ray 1 from the top surface of the film, the reflected ray R2 from the bottom surface of the air film. Now I'll be giving the names. So here's, this angle is what? If these two rays, if these two places were parallel, exactly parallel, then this is my R. So this is also gonna be R, but no, they are not parallel, so this can't be R. They are having some angle between them. Theta is the angle between them, so this angle can be R plus this theta, because with, if you bend it more, the more angle will come here. If you bend it less, the less angle will come here. So this angle got increased by this theta, so that's why this angle will be R plus theta. And here's I'm doing some geometrical, for the geometrical simplicity, I'm drawing some lines so that I can find out the path difference between them. So I'm drawing here a perpendicular line to this R1. So I'll be giving name. This is my A, this is my B, this is my C, this is my D. Now I'll be calling this as N. I will be drawing one more line perpendicular to the transmitted light ray, this one. So this triangle is having angle I. How come? Because angle of incident is equals to the angle of reflection. Okay, and we know this is 90 and this is also 90, so that's how this can be written as I. And similarly this is 90, so that's how this can be written as R. And here what I'm doing is I'm drawing this at this particular thickness, The film is having thickness T. So I'm drawing the mirror image of this BCD. Why am I doing all this thing? To find out the path difference between the ray 1 and the ray 2. So here's the point, we'll be calling it as E. So this is same as this thing. So this is the straight line, a normal to the surface, and this is also a straight line. And these two lines, I have just extended these lines. So it means this angle gonna be similar to this angle. This is also r plus theta. So I have everything I need to find out the path difference between ray 1 and ray 2. So the optical path difference is, so this distance AB and BC, this distance minus I have to do AN, then I can get the path difference between these. So after this particular point N and C, the lights are traveling equal distance. The story is all about here. Here's the path difference is there. This distance AB BC, this ray 2 is traveling longer distance. So I have to subtract this distance with AN. So in which medium this is all happening? So I'm giving this medium a refractive index mu. So you can have the wedge-shaped air film, wedge-shaped film made up of air, oil, water, any kind of. So depending on your requirement, if you're using oil or any other medium, so you can put the value of mu. So here's I'm putting, so I'm generalizing the thing, so I'll let it be just mu. So mu B AB plus BC, I have to subtract this distance from AN. So we can see from the geometry of the figure, the distance BC is exactly equal to the distance BE. Why? Because I've drawn just the mirror image of this thing. This triangle mirror image is this one. So that's how the distance is same. And the distance CD is equal to the distance DE. Okay. Now I can write the distance BC is equals to the distance BE. Now if I use this thing, I can write mu AB plus, instead of BC I can write BE minus AN. Now from triangle ANC sine I can be written as, this is the theta, here's the opposite is AN divided by hypotenuse, that is AC. Similarly from triangle A, so here's this point, I'm giving, name it as G, AGC, from that triangle AGC sine R can be written as the opposite AG divided by the hypotenuse GC divided by the hypotenuse. This is the 90 degrees, so this is the hypotenuse. AC is the hypotenuse. AC. If I divide, this is my 1 and 2. So by using this 2 equation, according to the Snell's law, mu is equals to sine I by sine R, and from that I can write this AC will get cancelled out. I'll be remaining with AN by AG. So AN can be written as mu AG. I'll be substituting this equation 3 and this 1. Instead of AN, I'll write mu AG. So the path difference is equals to mu. Now you can see the distance AB to BE can be written as AE. So instead of writing in parts AB, BE, I'll be writing directly A to E. So it is AE minus, now replace this AN with mu AG. Take mu outside, it's common, it will be AE minus AG. That this, I can do one more simplification. I have AE. So if I subtract from AE, if I subtract AG, I'll be remaining with GE. So here mu, if I subtract AE from AG, I'll be remaining with GE. It will be GE. So this is my Roman number 2. Now from triangle GCE cos R plus theta. So it is adjacent by hypotenuse. So this is the 90. So it means this is my adjacent side, GE divided by hypotenuse. This is the hypotenuse. CE is my hypotenuse. CE. So the distance CE can be written as CD plus DE. So the distance CD is how much? This is T. So as I told you, this is just the mirror image of this thing. So the mirror image means it will also have the same distance T. So this is also 2. It is also T. It means the distance CE can be written as 2T. So GE is equals to 2T cos R plus theta. So I'll substitute this thing, equation 4 in Roman number 2. I'll be getting the path difference. So the path difference is equals to 2 mu T. Already I had mu there. 2 mu T cos R plus theta is the path difference due to the path difference between R1 and R2. So there's one more path difference will come. This is not the true path difference. This is just the optical path difference. There is one more path difference will come, that is due to reflection due to the denser medium. There is a one more path difference will come. Here you see, this is the denser medium and this is the rarer medium. This is, I have here, if I call it as air or water or anything, this is the glass. So this is the denser medium and this is the rarer medium. So the ray 2 is getting reflection from the boundary of a denser medium. If any ray will get the reflection due to the denser medium, the ray will suffer the phase exchange of pi and the path difference of lambda by 2. So the additional path difference lambda by 2 is coming, so we have to subtract that thing with this path difference lambda by 2. True path difference between the ray 1 and ray 2, these ray 1 and ray 2. Now we can notice one thing is that this is exactly, it is almost the same path difference that which we got in the thin film, a constant thickness thin film. The only change is that this theta was not there in that equation, but here we have this theta. So if we somehow make it as 0, means if we make them parallel, we'll be jumping into the condition, we'll be jumping into the thin film whose thickness is constant. So this is the difference between that and this. Okay, now we will try to see what are the conditions to have a bright fringe and the dark fringe. Now for the condition for bright fringe, so the path difference should be n lambda, where n can take values from 0, 1, 2, likewise. So I have to equate this path difference here to this thing, 2 mu t cos r plus theta minus lambda by 2 is equals to n lambda. If I equate it like this, I can get what should be the thickness, what should be the refractive index, and what should be the angle of incidence to have the bright fringe. So here's 2 mu t cos r plus theta is equals to, it will be n plus 1 by 2 to lambda. So if the path, if the combination of mu, t and r, all these things are giving you some fractional value of lambda, then you will get a constructive interference, then you will get a bright fringe. The conditions are not as the fundamental conditions are because of this path difference lambda by 2, as you can see there. Now the condition for dark fringe, what is the condition for the dark fringe? It is n minus half lambda. We have to equate this thing, so dark fringe, and this is the condition for bright fringe. If the combination of this particular refractive index and thickness and the r theta, if these are all together are giving you some integer number, then it is sure that you are gonna get a dark fringe. This is all about interference due to wedge-shaped films. Thank you so much for watching. So stay tuned. Bye.